Good day, learners at home. You are once again welcome to another physics lesson on radio and television e-learning program of Ministry of Education, Kaduna State. My name is Hassan Buki. Today we are going to continue in our study on the topic electric field. Today we will consider electric field part 3. In our outline we have electric potential, capital letter V. We have electric potential difference between 2 points. Then we have relationship between electric field E and electric potential V. Now we look at electric potential, capital letter V in bracket. Now, if you remember in our study on gravitational field, we said in gravitational field we have only but forces of attraction. And these forces of attraction act on masses. They act between masses. Therefore, to separate between any two masses, work must be done against the field. Similarly, in electric field, we have forces of repulsion and forces of attraction. And therefore, to separate or to move charges in the field against the field, work must be done by an external agent in order to move charges against the field. Because we said in electric field, just like we saw in our part 1, that forces of repulsion or attraction acts between charges, while in gravitational force, forces of attraction act between masses. In the case of electric field, we have charges. Definition of electric potential. Electric potential V at a point is defined as the work done by an electric field in bringing a unit positive charge from infinity to that point. I take it again. Electric potential V at a point is defined as the work done by an electric field in bringing a unit positive charge from infinity to that point. Now, we look at electric potential difference between 2 points. And we said in electric potential difference between 2 points is the work done by an external agent in moving a unit positive test charge from one point to the other. Now, if we consider points A and B as shown in the diagram below, we have point A and point B, and this positive charge plus Q, plus capital Q, is at point A. Now at point B here we have another, this is a positive test charge plus small q, and we have the distance between the two charges as small letter r. Now, like we saw in our electric field intensity, that if a unit positive test charge is placed at the point, considering this charge which is positive, if we place a unit positive test charge here, this charge will repel it because they are of the same charges, the same sign, positive and positive, so there will be repulsion. So the field will be to the right, away from point B, that is away from plus small q, which is indicated by this arrow. This is our electric field. So the electric field will be in this direction to the right, away from plus small q. But this arrow here is showing us that this charge is being moved towards this plus capital Q. That means work is being done. We can see that it is in opposite direction. It is against the field. Therefore, it shows that an external agent is doing work here to move this positive test charge from point B to point A. So the potential difference between points A and B, given as V subscript capital AB in bracket, is given by the equation VAB is equals to W in bracket B to A. This arrow shows that work is being done in moving the charge from point B to point A. So VAB is the same as VA minus VB. That is the potential at point A minus the potential at point B, which is equals to the work done, capital W in bracket B to A. Where we have VA, we said is potential at point A, VB is our potential at point B. Now WB to A is our work done by an external agent in moving a unit positive charge from point B to point A, just like we saw in the diagram. Now, work done is given by, which is equals to charge times potential difference between A and B. Mathematically, we have W, capital W, to be equals to small q times V. We call it equation 1. Now we have W to be equals to Q. This V is VA minus VB. In general, we know that work done is the product of force and distance in the direction of the force. Therefore, our work done in this case, which we are considering electric field, our work done will be equals to electric force between capital Q and small q times the distance between capital Q and small q, which is given mathematically as work done W is equals to capital F times small r, and we call it equation 2, where capital F is our electric force between the charges. Small letter r is the distance between those two charges, capital Q and small q. If we equate equation 1 and 2, because from equation 1 we could see that W is equals to, on the right hand side, equation 2 is W. So the left hand sides are the same. So we have the left hand side are the same, so also the right hand side will be the same. And that is why we are equating equation 1 and 2. Now equating equation 1 and 2, we will have small q V to be equals to capital F times small r. But capital F, from our knowledge of electric field part 1, we saw that electric force, capital F, is equals to product of charges QQ over 4 pi epsilon naught r squared. So if we substitute for F in the above equation, we will now have small qV to be equals to capital Q times small q over 4 pi epsilon naught r squared times r over 1. Now, this q on the right hand side will cancel this small q. Small q on the right hand side will cancel small q on the left hand side. And small r here will cancel 1r here, and 1r will be remaining. So we'll have V to be equals to capital Q over 4 pi epsilon naught r. And that gives us equation 3. This is equation for our electric potential. Now from equation 1, if we make V the subject of the formula, we will have V to be equals to W over small q. which means work done over charge. And the unit will be what? Joules per coulomb, because work done is in joules, charge is in coulomb. So we have work per charge, which is joules per coulomb. The value of electric potential V at infinity is taken to be 0. Now, V is positive. When capital Q is positive, why? Because work is done in moving a positive charge from infinity to points in the field. And V is negative when capital Q is negative. This time there is an attractive force on a positive charge moved from infinity to points in the field. We say in this case that the field does work. In this case, it is the field that is doing the work, not an external agent. Both potential and potential difference are scalar quantities, which means they don't have direction. They only have but what? Magnitude. Now we look at the relationship between electric field intensity, capital E, and electric potential, capital V. We know that electric force is equals to charge, small q, times electric field intensity, capital E. So we have F mathematically, capital F to be equals to small q times capital E. And we call this equation 5. Again, if we equate equation 1 and 2, we will have small q V to be equals to capital F times R. Now, if we substitute F is equals to small q E into this equation here, we will now have small q V to be equals to small q capital E times small r. Therefore, we have capital V to be equals to capital E times small r. And in this case, our electric potential will be in Newton meters per coulomb. Now, E, electric field intensity, E, from here, if we make E the subject of the formula, we will now have capital E to be equals to V over small r. And in this case, our electric field intensity will be measured in volts per meter. Now, from equation 4 and equation 6, V has units as joules per coulomb, which we've seen already, and then Newton meter per coulomb. But the SI unit of potential is volts. That is its SI unit. Now, examples. Let's see how we can apply these equations in solving problems. Example 1A. Calculate the electric potential at points P and Q as shown in the figure below. B. Suppose the charge plus 9 microcoulomb is replaced by minus 9 microcoulomb. Find the electric potential at points P and Q. Now we have our positive charge plus 9 microcoulomb. We have point P, we have our point Q. The distance between point P and our charge plus 9 microcoulomb is 10 meters. And the distance between point P and point Q is 6 meters, which means that the distance between point Q and our positive charge, plus 9 microcoulomb, will be 16 meters. Solution: potential at point P is equals to V subscript P. We have our charge Q to be equals to plus 9 microcoulomb, which is equals to 9 times 10 raised to power minus 6 coulomb, because micro means 10 raised to power minus 6. Then we have Rp, which is the distance between point P and our positive charge plus 9 microcoulomb is 10 meters. Now, applying our formula for electric potential, we have Vp to be equals to Q over 4 pi epsilon naught Rp. Substituting in our value, we will have Vp, V subscript P to be equals to 9 times 10 raised to power 9 times 9 times 10 to power minus 6 all over 10. And that gives us V subscript P to be equals to 8.1 times 10 to power 3 volts, which means that the potential at point P is 8.1 times 10 raised to power 3 volts. Then at point Q, our potential, we have the distance between point Q and our charge, which is RQ, to be equals to 16 meters. So we have VQ to be equals to small q over 4 pi epsilon naught R subscript Q. So VQ will be equals to 9 times 10 raised to power 9 times our charge, 9 times 10 raised to power minus 6 over 16. And that gives us VQ to be equals to 5.06 times 10 to power 3 volts. That is the potential at point P. Now we have 2 points now. We will need to take the resultant to get our total potential. So V subscript PQ, that is the potential difference between point P and point Q, is equals to Vp minus VQ. So Vpq will be equals to 8.1 times 10 to power 3 minus 5.06 times 10 to power 3. And that gives us Vpq to be equals to 3.04 times 10 to power 3 volts. That means the potential difference between point P and point Q is 3.04 times 10 to power 3 volts. Now suppose we replace plus Q with plus 9 microcoulomb with minus. If we replace this plus 9 microcoulomb with minus 9 microcoulomb, we will now have our potential at point P to be Vp is equals to 9 times 10 to power 9 times. This time around, the negative sign will come in, all over 10, and we will have Vp to be equals to minus 8.1 times 10 to power 3 volts. Then at point Q, Vq will be equals to 9 times 10 to power 9 times bracket minus 9 times 10 raised to power minus 6 all over 16. And we will have Vq to be equals to minus 5.06 times 10 to power 3 volts. That is the potential at point Q. Now, our resultant, that means Vpq, that's the potential difference between point P and point Q, will be equals to Vp minus Vq. So we have Vpq to be equals to minus 8.1 times 10 raised to power 3 minus bracket minus 5.06 times 10 raised to power 3. Vpq now will be equals to minus 8.1 times 10 to power 3 plus, because if we open this bracket, minus times minus will be plus. So we have plus 5.06 times 10 raised to power 3. And finally, our answer will be Vpq to be equals to minus 3.04 times 10 raised to power 3 volts. Just like we have said in our statement before that, if Q is positive, V will be positive. If Q is negative, V also will be negative. Example 2, find the resultant potential at a point in free space, which is 0.1 meter, from a small charge of plus 1.5 times 10 raised to power minus 7 coulomb and 0.15 meter from a small charge of minus 2 times 10 raised to power minus 7 coulomb. Solution. We have our diagram. We have the two charges, Q1 and Q2. Now we have seen from our diagram that Q1 is plus 1.5 times 10 raised to power minus 7 coulomb, and the distance of Q1 from our point here, which is R1, is 0.1 meter. Then our Q2, second charge, is minus 2 times 10 raised to power minus 7 coulomb, and R2, which is the distance between our charge Q2 and this point, is 0.15 meter. Now, calculating V1 due to Q1, we will have V1 to be equals to Q1 over 4 pi epsilon naught R1. So V1 will be equals to 9 times 10 raised to power 9 times 1.5 times 10 raised to power of minus 7 over 0.1. And V1 will be equals to 13500 volts. That means 13,500 volts. So V2, that is second potential due to Q2, the second charge, we have V2 to be equals to Q2 all over 4 pi epsilon naught R2. Substituting in our values, we will have V2 to be equals to 9 times 10 raised to power 9 times bracket minus 2 times 10 raised to power minus 7 over 0.15. And V2 will be equals to minus 12,000 volts. Now our total potential, V total, will be equals to V1 plus V2. So we have V total to be equals to 13,500 plus bracket minus 12,000. That will give us V total to be equals to 13,500 minus 12,000, because if we open this bracket, we have plus times minus will be minus. So therefore, V total will be equals to 1,500 volts. And that is our answer. Now with this, we have come to the end of the lesson, but I will call on my second, Mr. Napoleon Kure, to come and review and then give you an assignment to do. Meanwhile, once again, I remain Hassan Buki. Till we meet in our next lesson, thank you.
You are welcome once again to the last part of our electric field as a topic we've started. And today we are looking at electric potential. As defined by my colleague, electric potential is the work done in taking a unit positive charge from infinity to a given point in a field. While the second part is electric potential difference. The word difference comes in to differentiate the fourth electric potential and electric potential difference. It simply means the work done is also a work done, but it is done in taking a unit positive charge from one point to another point this time around. Not like electric potential that does with from infinity to a given point. This one from a given point to another given point, and those are specific points. Now, we discovered that very important, we have 4 things to consider, or we have considered so far under this topic, electric field, just like gravitational field. Number 1, we have force, electric force. We have 2, electric potential, electric work done, and then we have electric field intensity. Electric force, capital F, is very important, is our basic formula, which leads to other ones, as F equals to QQ over 4 pi epsilon naught R squared, or F is equal to K, where that K is a constant taking care of 1 over 4 pi epsilon naught, and is equal to F, therefore equal to K QQ. The QQ there could be Q1, Q2, or whatever, over R squared. Now, our electric field intensity, as we have treated, is capital E equals to the same KQ, but over just one of the Q remain. That is, E is equal to KQ over 4 pi epsilon naught R square. In electric field intensity, Q, one of the Q is not there. Then for the electric work done is the reverse. We have W is equal to KQQ, that is Q square, or Q1, Q2 over R over R. That is just one R is missing there. Then our electric potential is V equals to KQ over R. So in the electric field, electric force, Q is there, 2 Q's are there, and our R square is there. Electric field intensity, One of the Q is not there, but the R square is there. That's the difference. Then electric work done is QQ. Two of the Q's will be there, one of the R is not there. Well, electric field potential, only one Q and only one R. Very important, that's the difference. Very important formula you take note of. With this, example have been solved and we have this assignment to give you so that you can keep yourself busy. Number one, we have a diagram of a test positive charge or a unit positive charge Q, small letter, of plus 2 times 10 to the power minus 8 coulomb, and a point A linearly the same with it as 10 meter. Another point B, which is 20 meter from that Q. Q is plus 2 times 10 to the power minus 8 coulomb. A is 10 meter from it, and point B is 20 meter from it. You have to calculate the potential difference between point A and point B. That is the question. Number two. A work of 30 joules is done in transferring 5 millicoulombs of charge from a point B to a point A in an electric field. Find the potential difference between B and A. References are 1. New School Physics by M.W. Anyakoha. 2. All-Inclusive Calculations in Physics by Solomon Dauda Yako. And then 3. Senior Secondary School Physics by P.N. Okeke and M.W. Anyakoha. These are the references you will get through and solve many of the problems. The 2 assignments given to you are inexhaustive. You go and get more of the exercises to solve. And our contacts remain Hassan Buki, 0806550464346. I take it again, Hassan Buki, 08065504346. Napoleon Kure, 08036362105. Napoleon Kure, 08036362105. You are advised to stay at home because coronavirus is real. While you remain safe and keep on learning until your exam period. Wish you the best. I remain Napoleon Kure. Till we meet in our next lesson. Thank you.